My name is Nico, and you're watching Frontline Reports, where we cut through the noise to bring you the stories that are quietly reshaping the world. There is a war being fought right now, and honestly, most people have no idea it is happening. No missiles have been fired, no soldiers have crossed any border, no battlefield appears on any map you have ever studied in school or seen on the evening news. The fighting is happening in government ministries and corporate boardrooms. It's happening in chemistry laboratories and cargo terminals. It's happening in mines buried deep beneath the mountain ranges of southern China, and in the policy documents circulating between Washington and Beijing that, well, never make the front page but are shaping the economic trajectory of the entire planet. The weapons in this war have names that most people cannot pronounce and would struggle to find on the periodic table. Dysprosium, terbium, yttrium, gallium, germanium, neodymium. They sound like characters from a science fiction novel, but they're as real as the smartphone in your hand, as real as the fighter jet flying overhead, as real as the wind turbine turning on the horizon. And whoever controls them controls something that no military force, no financial sanction, and no diplomatic pressure campaign can easily replicate or replace. The world's two largest economies, the United States of America and the People's Republic of China, have arrived at a confrontation over these materials that is unlike anything the modern global economic system has previously experienced. China has not merely reduced exports of these critical minerals to American companies. It has moved to cut them off entirely. And the consequences of that decision, playing out right now in real time across every sector that defines 21st century industrial civilization, are only beginning to be understood. This is the story of how we got here, what it means for defense, technology, and the clean energy transition, and what, if anything, the world can do about it. Before we can understand the full weight of what China's export restrictions mean, we need to spend a moment on the materials themselves. Because, the term rare earth elements gets thrown around in news coverage with very little explanation of what these substances actually are, what they actually do, and why their absence from the supply chain would create problems that cannot be quickly or cheaply solved. Rare earth elements are a group of 17 metallic elements that appear on the periodic table in a block that most people skipped over in chemistry class. Their names are genuinely unfamiliar to most people outside of materials science: lanthanum, cerium, praseodymium, neodymium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium, scandium, and yttrium. Reading that list aloud is enough to make most people's eyes glaze over. But understanding what these elements actually do in the real world is essential to understanding why their supply is one of the most consequential geopolitical questions of our time. Despite the name, rare earth elements are not particularly scarce in the Earth's crust. Actually, several of them are more abundant than copper or lead. What makes them genuinely rare and genuinely valuable is a combination of factors that makes extracting and refining them to industrial-grade purity extraordinarily difficult, expensive, and environmentally demanding. Rare earth deposits are rarely concentrated enough to mine economically. The refining process requires complex chemical separation techniques that generate significant toxic waste. Building and operating a processing facility capable of producing rare earth compounds at industrial scale requires years of development, massive capital investment, and highly specialized technical expertise that took decades to accumulate. And what do these elements actually do? Almost everything that defines the modern economy. Neodymium and dysprosium together are the critical ingredients in the most powerful permanent magnets known to engineering. Neodymium iron-boron magnets that provide the extraordinary magnetic force needed to drive the electric motors in electric vehicles and the generators in wind turbines. Without these magnets, the leading technologies of the clean energy transition simply do not work at the performance levels that make them commercially viable. Terbium and europium are essential for the phosphorescent materials that make flat screen displays and energy-efficient lighting produce accurate, vivid color. The screen you are watching this video on almost certainly contains materials derived from these elements. Yttrium is used in the ceramic coatings that protect jet engine components from the extreme temperatures generated by combustion. Without it, jet engines degrade far more rapidly. It also appears in medical imaging technology, contributing to diagnostic equipment that saves lives in hospitals every day. Lanthanum is a critical component in the catalysts used by petroleum refineries to process crude oil into usable fuel. Gadolinium is used in the contrast agents injected into patients before MRI scans. The magnetic resonance imaging technology that allows doctors to detect tumors, diagnose neurological conditions, and examine soft tissue without radiation. Then there is the broader category of critical minerals. Materials that are not technically rare earth elements, but that are equally essential and equally dominated by Chinese production and processing. Gallium and germanium are foundational to semiconductor manufacturing at the frontier of performance. Gallium-based compound semiconductors power the 5G wireless infrastructure being deployed across the world, the satellite communication systems that civilian and military users depend on, and the high-frequency radar systems that are central to modern air defense. Germanium is essential for the fiber optic cables that carry the internet's data traffic, and for the infrared optical systems used in military night vision and thermal imaging equipment. Antimony is used in flame retardants found in electronics and textiles, in the ammunition manufactured for military and law enforcement use, and in the night vision equipment that modern military forces consider essential battlefield technology. Tungsten, one of the hardest naturally occurring materials known to science, with the highest melting point of any metal, is used in cutting tools for industrial manufacturing, in electronics, and in military-grade armor and munitions. Not one of these applications is optional. Not one of them can be quickly or easily served by alternative materials. These are the non-negotiable building blocks of contemporary industrial civilization. And China, through a combination of geological fortune, strategic foresight, environmental tolerance, and decades of patient investment, controls a proportion of the global supply that gives it leverage unlike any other commodity relationship in the modern world. The United States Geological Survey, the definitive authority on American mineral resource assessment, estimates that China accounts for approximately 60 to 70% of the world's annual rare earth mining output. But mining is only the first stage of the supply chain. The more decisive measure of control is in processing and refining, the transformation of raw ore into the purified compounds and alloys that manufacturers can actually use. At that stage, China's dominance is far more overwhelming. By the most credible estimates, China processes between 85 and 90% of the world's rare earth elements, including a significant portion of the ore that is physically mined in other countries. That last point deserves particular emphasis because it is where most people's intuition about this issue goes wrong. Even if a rare earth mineral is physically extracted from the ground in Australia, the United States, Canada, or Brazil, the overwhelming probability is that it will be shipped to China for processing before it can be incorporated into any industrial product. The refining infrastructure, the chemical plants, the separation facilities, the technical expertise that transforms raw ore into usable material is concentrated in China to a degree that has no parallel in any other industrial supply chain. This is the leverage that China possesses, and this is the leverage it has now chosen to deploy. The current crisis did not emerge from nowhere. It's really the culmination of a deteriorating relationship between Washington and Beijing that has been building for years across multiple dimensions. Trade disputes that escalated into tariff wars, technology restrictions that struck at Chinese industrial ambitions, accusations of intellectual property theft, deepening disagreement over Taiwan's status, and, these competing visions of what the global order should look like in the 21st century. The relationship that defined global trade and economic growth for 3 decades. A relationship built on the assumption that deep commercial interdependence between the world's two largest economies would create mutual incentives for stability, has been fracturing. And honestly, the fracture accelerated dramatically with a specific action by the United States government that Beijing interpreted not as a defensive security measure, but as a declaration of economic war. In a move that sent immediate shockwaves through global markets and diplomatic channels, the U.S. government announced sanctions targeting 136 Chinese companies. The list was not composed of obscure or peripheral businesses. These were firms deeply embedded in China's most strategically significant industrial sectors: drone manufacturing, advanced electronics development, artificial intelligence research, and the production of components that American officials alleged were being channeled into Chinese military programs, with implications for regional and global security. The legal and regulatory framework for these sanctions drew on a body of American national security law that allows the U.S. government to effectively cut designated entities off from the American financial system, from American suppliers and technology, and from any business relationship with companies that themselves operate within the United States. For companies whose products, components, or financing touch the American economy in any way, which, in the interconnected global economy, describes a very large number of Chinese companies, being placed on this list is a severe commercial and operational blow. Washington's stated rationale centered on China's military-civil fusion strategy, the national policy framework through which Beijing deliberately integrates commercial enterprise with military capability, ensuring that civilian technology development contributes to military modernization and vice versa. American officials argued that under this framework, ostensibly commercial Chinese companies in sectors like advanced electronics and artificial intelligence are, in practice, contributors to Chinese military programs that represent genuine threats to American security and the security of American allies. Beijing's interpretation of these sanctions was fundamentally different. From the Chinese government's perspective, the sanctions were not a legitimate defensive security response to genuine threats. They were the latest and most aggressive manifestation of a sustained American strategy of technological containment, a deliberate effort to use economic and regulatory tools to prevent China from advancing to the frontier of the technologies that will define the next era of economic and military competition. In this reading, the United States, having enjoyed decades of technological and industrial dominance that it treats as the natural order of things, is attempting to maintain that dominance not through superior innovation, but through the suppression of Chinese capability. China's response came in the measured, bureaucratic language that Chinese government communications characteristically employ. But the substance of the response was anything but measured. The Ministry of Commerce, coordinating with other regulatory bodies, announced sweeping export controls on a range of critical minerals and rare earth elements destined for the American market. The restrictions covered gallium, germanium, antimony, and several categories of rare earth elements, materials that sit at the foundation of American defense manufacturing, semiconductor production, electric vehicle supply chains, and the renewable energy infrastructure that the United States has committed to building at enormous scale. Critically, this was not China's first move in this direction. Export restrictions on gallium and germanium had been announced in mid-2023, sending a deliberate signal to Washington about China's willingness to use its mineral supply chain dominance as a geopolitical instrument. Those early restrictions were, in retrospect, a carefully calibrated warning, an opening move in a strategic sequence rather than a terminal action. The more comprehensive restrictions that followed the 136 company sanctions represented a significant escalation, a shift, as analysts described it, from signaling to serious deployment of the mineral weapon. The consequences of China's export restrictions did not take time to materialize. Across three distinct and critically important sectors of the American economy, the implications were immediate, alarming, and in important ways, genuinely difficult to address in the American defense industry was the first to sound the alarm loudly and urgently, because for defense contractors and Pentagon planners, this was not a new concern being encountered for the first time. It was a documented vulnerability that had been acknowledged, studied, flagged in official reports, and never adequately resolved, now transitioning from a theoretical risk to an active operational constraint. Rare earth elements are not peripheral components in advanced military systems. They are foundational. The F-35 Lightning II, the most sophisticated strike fighter aircraft in the American arsenal, a platform that represents decades of development and hundreds of billions of dollars of investment, requires approximately 900 pounds of rare earth materials in each aircraft. Those materials appear in the radar systems that allow the jet to detect threats beyond visual range, in the powerful permanent magnets that drive actuators controlling flight surfaces, in the electronic warfare systems that can jam enemy radar and communications, and in the engine components that deliver the performance characteristics that make the F-35 competitive against advanced adversary aircraft. The Navy's newest surface combatants, the Arleigh Burke-class destroyers that form the backbone of American naval surface warfare capability, incorporate rare earth elements in their propulsion systems, in the powerful Aegis radar installations that provide fleet air defense, and in the weapon systems that give them offensive capability. The Army's Patriot missile defense systems, used to protect American forces and allied populations from ballistic missile attack, currently deployed in multiple active conflict zones, rely on rare earth materials in the guidance systems that give them the precision needed to intercept fast-moving incoming threats, and those are the currently operational systems. The next generation of American military capability, hypersonic missiles capable of reaching targets at speeds that defeat existing air defense systems, advanced electronic warfare platforms, directed energy weapons, all depend on rare earth elements and the other critical minerals that China has now restricted. The Department of Defense has published multiple assessments over the years acknowledging precisely this vulnerability. Billions of dollars have been committed to developing domestic alternatives and to building strategic stockpiles that could buffer against supply disruptions. But strategic stockpiles are, by their nature, finite. They buy time. They do not solve the underlying supply chain problem. And the development of domestic rare earth processing capacity, sufficient to replace Chinese supply while underway, remains years from reaching the scale needed. In direct testimony before congressional committees, senior defense officials have stated something that deserves to be quoted carefully and taken seriously. For certain specific rare earth compounds, particularly the heavy rare earths, dysprosium and terbium, that are essential for the high-performance permanent magnets used in advanced military systems, there are currently no processing facilities anywhere outside of China operating at the scale needed to meet American defense industry demand. That is not a future problem. That is the current reality. The technology industry's exposure to China's critical mineral restrictions is equally profound, though its character differs from the defense sector's vulnerability in important ways. Gallium and germanium are not supplementary or optional components in semiconductor manufacturing. They are foundational to specific categories of semiconductor performance that have no straightforward substitutes. Gallium-based compound semiconductors, materials like gallium nitride and gallium arsenide, are essential for the chips that power fifth-generation wireless infrastructure, satellite communication systems, and the high-frequency radar and electronic warfare systems that both civilian telecommunications and military operations depend on. These are not legacy technologies that could be phased out. They are the enabling materials for the communications infrastructure being built right now to support the next generation of connectivity. Germanium's role in fiber optic cables, the physical infrastructure through which the vast majority of the world's internet traffic travels, makes it equally critical. The cables that carry data between continents, between cities, and increasingly within cities depend on germanium in the production process for the high-purity glass fibers that carry light signals. Restricting germanium supply does not immediately stop existing fiber networks from functioning, but it significantly complicates the expansion of fiber infrastructure at a moment when demand for bandwidth continues to grow rapidly. For semiconductor companies, the supply chain implications ripple outward from manufacturing directly into the geopolitical competition over technological leadership. The advanced chips at the frontier of artificial intelligence development, quantum computing research, and military electronics all depend on materials whose supply China has now chosen to restrict. For an industry already navigating the disruptions created by previous supply chain crises, and by American export controls on advanced chip technology to China, the addition of Chinese mineral supply restrictions creates a genuinely complex strategic environment. Perhaps the dimension of China's export restrictions that will be most broadly felt by ordinary people around the world, not just in the defense establishment or the technology industry, but by anyone who drives a car, pays an electricity bill, or breathes the air in any major city, is the impact on the clean energy transition. The United States has committed, through the Inflation Reduction Act signed into law in 2022, to one of the most ambitious clean energy transitions in American history. Hundreds of billions of dollars in subsidies, tax credits, manufacturing incentives, and infrastructure investment are designed to accelerate the deployment of electric vehicles, offshore and onshore wind power, solar energy, and the battery storage systems that make renewable electricity reliable. The strategic logic of this investment is not only environmental, it is economic and geopolitical, designed to ensure that the supply chains supporting the clean energy economy are rooted in America and its allies, rather than in countries that Washington has identified as strategic competitors. The collision between this strategic vision and the reality of rare earth dependence is as stark as it is uncomfortable. Every electric vehicle powered by a permanent magnet motor, which describes the dominant majority of the leading EV models currently on the market from virtually every major manufacturer, requires neodymium iron boron magnets that incorporate neodymium and, at higher performance levels, dysprosium. These magnets provide the power density and thermal stability that make EV motors competitive in terms of range efficiency and performance. No currently available alternative magnet technology matches their performance characteristics at comparable cost and weight. American automakers are in the middle of the most consequential industrial transition in their history. Ford, General Motors, and Stellantis are each investing tens of billions of dollars in EV production capacity. Newer entrants like Rivian and Lucid have built their entire business models around electric vehicles. Tesla, the company that defined the modern EV era, has been working for years on motor architectures that reduce rare earth content, but has not eliminated the dependency entirely. If rare earth supply from China is meaningfully constrained over an extended period, the cost structure of EV production deteriorates, supply chains face disruption, and the already difficult economics of scaling up American EV manufacturing become substantially more challenging. Offshore wind power, a cornerstone of the clean energy plans of both the Biden administration and most European governments, is particularly exposed. The most powerful offshore wind turbines, designed to maximize energy generation from slower-moving ocean winds, depend on permanent magnet generators that use rare earth materials. The United States government's target of deploying 30 gigawatts of offshore wind capacity by 2030 was built on assumptions about reliable material supply that China's export restrictions have thrown into genuine question. The uncomfortable truth at the center of this story, the truth that makes this crisis not just a Chinese aggression story, but also an American self-inflicted wound story, is that the United States did not stumble accidentally into rare earth dependence. It arrived here through a sustained series of deliberate economic choices that prioritize short-term cost efficiency over long-term strategic resilience. And understanding how that happened is essential to understanding whether, and how, it can be reversed. For much of the mid-20th century, the United States was not just a consumer of rare earth elements, it was a major producer. The Mountain Pass mine in the Mojave Desert of California was, at its peak, the single largest rare earth producer in the entire world. American companies held leading positions in the technical knowledge and industrial processes for rare earth extraction and refining. The expertise, the infrastructure, and the commercial ecosystem that supports a domestic rare earth industry existed in America within living memory. Then, beginning in the 1980s and accelerating through the 1990s, China entered the rare earth market in a manner that fundamentally altered the global competitive landscape. The Chinese government made a strategic decision, one that reflected a clarity about the long-term geopolitical value of mineral supply chain control that Western governments and corporations largely failed to match, to develop China's rare earth industry as a national strategic priority. That decision was backed by substantial government subsidies, by environmental standards that permitted processing practices that would not have been